Over the course of more than 200 videos on YouTube, I've solved so many integrals. I've solved integrals having wild structures. I've solved integrals that resulted in these beautiful closed forms you often see here. And it's always great fun. Integrals are just wonderful things to play with. But today I want to talk about a very special integral at the very core of mechanics. And the principle behind this integral is one of the fundamental principles at the heart of physics itself. This integral that we call S for reference purposes has a pretty interesting name. It's called action. So yeah, that's cool. The action integral is an integral over time of a very special function L called the Lagrangian of the system. And the Lagrangian of a system is defined as its total kinetic energy minus its total potential energy. Now, before we get to the analysis of this integral, let me get you acquainted with some terms that get thrown around quite often in physics. One of these important terms is degrees of freedom. By degrees of freedom, I mean the number of independent quantities I need to describe the system's position. And by system's position, I mean the positions of all the particles forming the system. So in the case of a system consisting of n particles, I'm going to need n radius vectors. And each radius vector has 3 independent components, right? So that means this system has 3n degrees of freedom. The number of degrees of freedom of a system also depends on the constraints the system is facing. For example, if you have a system consisting of 2 particles, then this system has 6 degrees of freedom. But what if those 2 particles are bound together in a diatomic molecule? In that case, we see that the coordinates of the 2 particles are related by some distance function. So the distance between these 2 particles is fixed and given by some distance formula that is a function of x1, x2, y1, y2, and z1, z2. So that means given any 5 of these coordinates, the distance between the 2 particles can be used to determine the 6th coordinate. So instead of having 6 degrees of freedom, you actually have 5 degrees of freedom in this case. Of course, one can generalize this by saying that if we have k number of constraint functions, then it's possible to eliminate k variables from the total number of degrees of freedom, and thereby our system will have 3n minus k degrees of freedom. Okay, cool. And so far we've been talking in terms of Cartesian coordinates. But we don't have to always talk about Cartesian coordinates. Any coordinate system will work as long as it takes care of the degrees of freedom. For example, assume you have a single particle. A single particle has 3 degrees of freedom, and they can be represented in terms of the coordinates x, y, and z in Cartesian coordinates, or we could switch to polar coordinates and describe the particle's position using the variables r, theta, and phi. In both cases, we see that we have 3 degrees of freedom. And this motivates us to study physics using generalized coordinates. So instead of limiting ourselves to either Cartesian or polar coordinate systems, we could form generalized coordinates, and corresponding to n degrees of freedom, we can represent them by q1, q2, q3, all the way up to qn. Now, the mere specification of coordinates at a certain instant of time, called a t1, isn't enough, because that's not enough information to determine the state of the system at a future time t2. And experience tells us that in order to be able to predict the behavior of the mechanical system, we need not only the coordinates as functions of time, but we need their time derivatives. That forms the set of generalized velocities that we denote by dots. The dots mean time derivatives. So we have q dot 1, q dot 2, q dot 3, all the way up to q dot n. And I'm representing the set of generalized coordinates as qi of t, and the corresponding set of generalized velocities as q dot I of t. This set of quantities forms what's called the mechanical state of the system. And we know that given the mechanical state at a certain instant of time t1, we could determine the mechanical state at some other instant of time, t2. Now, what is that all-important principle I kept talking about at the beginning of the video? Well, that's something called Hamilton's principle. And what does this principle say about the motion of mechanical systems? Well, if you have a mechanical system having some initial position described in terms of the generalized coordinates as qi at t1, and because of the motion of the particles involved, the system evolved to a final position given by qi at t2, then this evolution of the system is obviously going to be described by the generalized coordinates qi as functions of time. Now, this function is something we call a path. The thing is, there are infinitely many functions or paths that start at this initial position and end at this final position. So out of all the possibilities, what is the path chosen by the system? That's the question answered by Hamilton's principle. Hamilton's principle states that the path chosen is the one that'll minimize the action integral S. In other words, the action integral, defined as the integral from t1 to t2 of the Lagrangian, attains a minimum value on the actual path followed by the system. Okay, that sounded extremely cool, but honestly wasn't really that helpful, right? Let me explain. Our goal is to minimize this function S defined in terms of an integral of a function L. And this function L, recall, is the difference between kinetic and potential energies. So this means that L is a function of the generalized coordinates, the generalized velocities, and possibly of time as well. And bear in mind, I'm using the index notation here to denote the entire set of generalized coordinates as well as generalized velocities. So it's understood that I here varies from 1, 2, 3, all the way up to n, the total number of degrees of freedom. This is just a much more convenient way of writing it. Okay, so we know exactly how to minimize a function y equal to f of x. We know exactly what to do. We calculate the derivative and set it equal to 0. How on earth do we minimize this function as defined in terms of an integral? And the function we're integrating is a function of quite a few variables. Well, that's the subject of a very powerful tool called the calculus of variations. And I'm going to demonstrate its use for minimizing the action integral. I'm going to call the chosen one among all the possible paths as qi of t, and bear in mind that this is a function we're talking about. And all the other paths or functions are different from qi of t. So let's parameterize this difference by introducing a parameter alpha. So we introduce it as an input to the function qi. And for alpha being 0, we should get the chosen path. The chosen path does not differ from the chosen path. So we have qi of t and 0, plus some variation from qi of t. The variation from the chosen path can be written as alpha times some function lambda I of time, where it's understood that lambda I should have continuous first and second derivatives because, of course, we're not interested in pathological paths, right, where you have discontinuities in velocities or accelerations, or the velocities and accelerations are not defined there, blah, blah, blah. We want actual physical reality here. This is a mechanical system moving from one state to another. So yeah, lambda should have continuous first and second derivatives with respect to time. Okay, cool. So under this parameterization, I can treat S now as a function of alpha. So S is now the integral from t1 to t2 of L, which is a function of qi of t and alpha, q dot I of t and alpha, and time as well. And now to minimize this function, we differentiate s with respect to alpha and apply the usual differentiation under the integral sign you've seen me do so many times here on the channel. So in that case, we're interested now in the partial derivative with respect to alpha of the Lagrangian L, and using the chain rule, we're gonna get this structure here. Okay, so you have n number of generalized coordinates and velocities, so the chain rule is gonna give you the sum from I equals 1 to n of partial L by partial Q times Qi, partial Qi by partial alpha, plus partial L by partial Q dot I times partial Q dot I by partial alpha, integration with respect to t. Okay, cool. And of course, we can switch up the order of the summation and the integration operators. So we have the sum from 1 to n of the integrals from t1 to t2 of partial L by partial Qi times partial Qi by partial alpha plus partial L by partial Q dot I times partial Q dot I divided by partial alpha, and integration with respect to t. And it's the integral of the second term here that I'm interested in first. So let me just single this out as the integral from t1 to t2 of partial L by partial Q dot I, and Q dot is the derivative of Qi with respect to t. So I could write this as a mixed second partial of Qi with respect to time and alpha. Okay, great. And now I have a nice structure for integration by parts because I can integrate this thing with respect to t. So on integration, I'm going to get partial Qi by partial alpha times partial L by partial Q dot I, and the limits of integration are t1 and t2. That's quite important, and I need some more writing space here now. Oh, terribly sorry about that. Much better. Oh, wait. There we go. Minus integral from t1 to t2, we have this integrated function that's partial Qi by partial alpha times the time derivative of the second function that's partial L by partial Q dot I. Now to evaluate this term at the given limits. So what exactly is this derivative of Q with respect to alpha? Remembering that Qi as a function of time and alpha is defined as Qi of t0, that's the chosen path, plus alpha times a function lambda I of t. So that means that partial Qi by partial alpha is just the function lambda I of t. Now here's the deal. All the paths, including the chosen path, start and end at exactly the same values. The starting and ending points of each path are the same. So that means for t1 and t2, we need lambda I to be 0. Because only in that case will all possible paths and the chosen path end at the same points. Okay, so that means plugging in the limits t1 and t2, we get lambda I of t2, which is 0 minus 0, so we get a big fat 0, and this thing cancels out quite nicely. So this means that the integral I sub 2, let's call it, I sub 2 equals negative integral from t1 to t2 of partial Qi by partial alpha, that's an alpha, not an x over there, okay, by partial alpha, times the time derivative of partial L by partial Qi dot, Q dot I, that is, dt. Okay. All we have to do now is plug it back into the sum and integral structure. So we have the sum from I equals 1 to n of the integrals from t1 to t2 of partial Qi by partial alpha times partial L by partial Qi minus now partial Qi by partial alpha times the time derivative of partial L by partial Q dot I. Okay, great. That means we can factor out this term of partial q by partial alpha. So we have the sum from I equals 1 to n of t1 of the integrals from t1 to t2 of partial L by partial qi minus d by dt partial L by partial q dot I all times partial qi by partial alpha integration with respect to t all being equal to 0, where of course the derivative being equal to 0 signals that we have a stationary value. Okay, so what we have here is this entire structure being equal to 0. And we know that the QIs are independent of each other. They're independent of each other, meaning that their alpha derivatives are also independent of each other. So we have this entire structure involving independent quantities being equal to 0, and that's possible only when the coefficients of those independent quantities are 0 themselves. So what we conclude is partial L by partial qi minus d by dt of partial L by partial q dot I being equal to 0 for all I from 1 to n. These are the Lagrangian equations of motion, and you can use them to derive the equations of motion for any mechanical system once you've defined a set of generalized coordinates and the Lagrangian of that system in terms of those generalized coordinates and velocity. As a sort of reality check on whether or not the Lagrangian equations of motion do indeed lead to the usual laws of mechanics we're familiar with, let's see how the Lagrange equations lead to Newton's second law. So for that, our system of generalized coordinates is just the usual Cartesian system, and we're considering a particle of mass m in a force field, and because of its position in the force field, it has a potential energy, which is a function of the particle's position, and possibly of time. For example, if we consider the motion of an asteroid in the gravitational field of a star executing some celestial motion itself, then yes, you do get a time-dependent potential, and velocity-dependent potentials are actually pretty common in electrodynamics as well. But right now we're just keeping the case simple. The kinetic energy of the particle is half mv squared. Okay, great. So what do the Lagrange equations look like in this context? Well, we have partial L by partial r minus d by dt partial L by partial v being equal to 0. Okay. Now, L equals t minus u, and t here is independent of position, so that means partial L by partial r is just negative partial u by partial r, and writing this on the right hand side we have d by dt, and because u is independent of velocity we have d by dt of partial t by partial v. Now wait a minute, what exactly does differentiating a scalar field with respect to some vector even mean? Well, that means we differentiate with respect to the components and just attach the unit vectors with it. So let me just expand the structure completely. Oh wait, terribly sorry about that. We have this partial z downstairs, z cap. Wait a second, isn't this exactly what the gradient of u looks like? So yeah, we have grad u. So this implies that we have negative grad u being equal to d by dt of partial t by partial v, which can be expanded as 1/2 of mv squared. So 1/2 of m is just a constant. I'm writing that out here. And if you differentiate v squared with respect to the velocity vector v using the same expansion I've outlined above, we get twice, oh, forgot the mass of the particle here, we get twice the velocity vector itself. So we have d by dt, and this results in twice the velocity vector. So the 2's cancel out quite nicely, and we're left with m times dv by dt, which we recognize as the acceleration. And of course, the negative gradient of the potential energy function is the force vector. So we have force equal to mass times acceleration, and we've derived Newton's second law. Wow, that is pretty cool. That is extremely cool. I'm going to be doing a few more videos on analytical mechanics to show just how cool the Lagrangian and Hamiltonian formalism is. And in the next video, we're probably going to be talking about conservation principles, which are extremely cool as well. So anyway, I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.